Okay, so remember our equation's F equals ma, and we were talking about what happens when we change our variable. So we started off with our control here, and then we increased the mass, which, how did that affect the acceleration? Right, because the same amount of force acting upon a greater mass, your acceleration is going to go down. So what type of relationship was that? Inversely proportional. Okay, so what if we do this? What are we doing with the mass? Okay, yeah, we're decreasing the mass. Our force is the same, so what is that going to change? And that's going to increase, right? So it's going to go fast. All right. So what have we changed here? Okay, so we're increasing the force now, right? Because our arrow is bigger. Going back to this arrow. Okay. So we increase the force. What happens to the acceleration? Yeah. So go back to this. So if we increase the force, what's going to happen to this acceleration? It's also going to increase, right? So our mass and acceleration are inversely. One goes up, the other one goes down. But force and acceleration, you increase the force, it's going to increase the acceleration, so those are directly proportional. Okay? So that's your second relationship at the bottom there. And what do you think the relationship between force and mass? Well, let's look at this. So if we keep the acceleration where it is, increase the force, acceleration is going to be the same, or I guess it's better to use mass. If we increase the mass, acceleration is going to stay the same. What's going to have to happen to the force? It's going to have to increase, right? So if we get a bowling ball here, which increases the mass, in order to move that at the same acceleration, and this is going to stay, acceleration is going to stay the same, our force has to increase. Okay? So force and acceleration are directly proportional as well. So it all depends on which side of the equal sign they are, right? If they're on opposite sides, remember they have to equal each other. They're on opposite sides of the equal sign, so if one goes up, the other one has to go up to equal each other. But if they're on the same side, one goes up, the other one has to go down to equal, in this case, the force. Okay? If an astronaut throws a dumbbell in space, what would be the result? Okay. Anyone know what constellation that is? Big Dipper, a prize. So we have our astronaut who's going to throw a dumbbell. Okay, he's floating in space. So what's going to happen? Okay, it's going to float. What else is going to happen? It'll keep going. It'll keep going. What else is going to happen? The astronaut is going to be pushed away. Why? Why? What is the third law? Third law? Newton's third law? I know, that's what I'm asking. Equal and opposite reaction, right? So that is our third law. Bless you. Okay, next let's talk about weight and apparent weight. Now, what did we say weight was? Right, the force of gravity. How much gravity affects a mass. Right, so we have a guy standing in an elevator. Isn't that awesome elevator music? So first of all, we need to determine how much he weighs. So he has a mass of 100 kilograms. So how are you going to determine how much he weighs? What's the one formula that we've used? No, the one formula from this. F equals MA, right? F equals MA. So we're looking for force of weight. Okay, what's the mass? 100 kilograms. What's the acceleration? Why 10? Because that's gravity. 10 meters per second squared. Okay? So to find weight, you just take the mass and multiply it by 10 meters per second squared if you're on Earth. Okay, in this case we are. So, how much does our guy weigh? 1,000 newtons. Okay? So that's what we just did orally. So force of weight, F sub W. Okay. F equals MA. Of course, we are substituting A for G, right? In this example. In our G, our acceleration is going to be 10 meters per second squared. Multiply those two, and we get 1,000 newtons. So this guy weighs 1,000 newtons. Now, it should be pointed out that he weighs 1,000 newtons standing in an elevator that is not moving. Right? If the elevator moves, then we're going to have a different weight. So start thinking about that. Start thinking about when you have been in an elevator, when it's going up versus when it's going down. Think of what happens to your weight. Okay? So, first example, if the elevator is going up, okay? Elevator's going up. What do you guys think? Same, more or less? More. More, less? If you think it's more, tell me why. Why do you think it's more? Alex. Ooh, very good. So going the opposite direction of gravity, of its weight. Okay? So his weight is pulling down, and he's going up. You get the same sensation on a roller coaster. When you go down, you feel one thing. Then when you go up the other side, right, you feel really heavy, right? Because you are going against gravity. Okay? So in that case, guy in the elevator will weigh more. Because it is, you have to take the acceleration of the elevator and add it to your acceleration of gravity. So you're no longer going 10 meters per second, right? It's 10 meters, or pardon me, 10 meters per second squared gravity, but you're going that plus your acceleration upwards, right? And then you're going to take that and multiply it by your mass. So what about going down? Okay, you're going with gravity. Okay, so you're falling with gravity. So you're going to subtract that from gravity. So the rider will weigh less. Okay. So that's the feeling on the roller coaster. You get to the very top, and then you go straight down, and you feel like you're floating in your chair. You feel like you can fly right out. Okay? Your stomach feels all weird. Okay, what about... Oh, that animation's not going to work. Guy just hanging out. And then... Someone's cut the cable! How much is he going to weigh on the way down? He won't. He will be weightless. Why? Because he's traveling with gravity, the same acceleration as gravity. Okay? So it'll be 0. And he will be weightless. Now, in all these examples, we are ignoring things like air resistance. All right. You guys heard of the Vomit Comet? Yeah, the airplane that the astronauts train in. And what it is it's a big airplane that they've taken all the seats out of the middle, and it travels like this. Okay, so it goes up, 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 these elliptical patterns, and then it goes down like this. So from this period, and I don't know, I think it's only 15 seconds, 20 seconds or so. They are going with gravity, so they are weightless inside. Okay, so for those brief instances, they can practice in a weightless environment on this airplane, but they can only do so for those few seconds, and then they have to buckle down real quick, because right here, what's going to happen? They're going to have to go back up, and they're going to be squished against wherever part of the plane they're on. So there's a constant up and down, up and down. That also tests how well their stomach is. because a lot of people end up losing their breakfast. Bless you. They also have private, or I forget how much it costs, but it costs us some substantial money. But you can go on the Vomit Comet and ride the craziness. All right, what about sideways? That'd be the same, right? Because it's not going up against gravity or down with gravity. So sideways, way the same. Okay, our summary. So what's our first law? Which is what? Resistance to change. Net force. It's law 2 and 3, equal and opposite. Okay, those are our standard. Three laws.